Welcome back, listeners, to the Dairy Science Digest. This is a podcast designed to bring the Journal of Dairy Science straight to the ears of dairy producers. I'm Reagan Globule from the University of Missouri Dairy Team, and today we're joined with Dr. Andres Contreras, and he's featuring his team's article that's actively in press currently. And for those of you listeners out there, there's going to be a bit of cautioning this month, a forewarning, so to speak, that we're delving deep this month into the deep end of biochemistry and the genetic control of that fresh cow that you know has challenges. The title of the article that we're studying today is Lipopolysaccharides, an induction of lipolysis and insulin resistance in the adipocyte tissue of dairy cows. And really what that boils down to, and I can't wait for the conversation to talk about how we can better understand why fresh cows fail so that hopefully we can craft management solutions and enable our cows to sail through these challenges. So, Dr. Contreras, could you please introduce yourself to our listeners?
Oh, thank you, Reagan, for the invitation. My name is Andres Contreras. I work at the Department of Large Animal Clinical Sciences at Michigan State University.
Very good. So could you talk us through a little bit about what made you want to study this perspective, or what made you chase down the tissue samples of fresh cows?
Okay, so our research focuses on the fat. And as you know, cows have negative energy balance in the first 2-3 weeks after calving. And to actually cope with that negative energy balance, they start to mobilize fat. And that's why we see our cows get thinner and thinner and thinner during the first 2-3 weeks after calving. Usually they lose about 10% of the body weight. And that body weight loss is largely explained by a reduction in the fat depots. So fat mobilization, it's very important in how cows address all the metabolic requirements of the transition period.
And so the way you tested that, let's run through a little bit. You grabbed some subcutaneous fat samples and you looked at the prepartum cow about 11 days prior to calving. And then you studied again at day 6 in milk and day 13. So a week and 2 weeks later, we're looking at the fat composition of those animals transitioning through calving. Could you tell us a little bit about how you sampled those tissues?
Okay, so yeah, we collect samples from the flank area on the right side, a very small incision, and we usually harvest about 5 grams of fat. And with that fat, what we run is assays that actually characterize how is that fat is responding to the energy requirements of the cow. So we induce lipolysis, which is the breakdown of fat. And we test for lipogenesis, which is the buildup of fat. So around parturition, the rate of lipolysis, the breakdown of fat, surpasses the rate of lipogenesis, which is the building of the fat. And that's why cows lose weight. So what we want to see in that serial sampling of the fat is how that dynamics changes and how that was affected by exposure to bacterial component, which is LPS.
And so the LPS, that's going to be the challenge, the endotoxin challenge. The LPS is really kind of trying to expose that tissue that you've collected in the laboratory to the challenge that the dairy cow feels in the barn. Could you tell us a little bit about what would be a common endotoxin that a fresh cow would be exposed to that you were trying to replicate here in the Petri dish?
Yeah, great. So our model, what tries to do is to expose the fat to what it would be an infection in vivo. So we do it in a Petri dish. We use LPS because those are remnants of bacteria, usually gram-negative bacteria that are the cause of common diseases right around calving. Think about retained placenta, think about metritis, think about toxic mastitis, think about pneumonia. When the cow is able to control the infection, it actually destroys the bacteria, and the remnants, which are the LPS, lipopolysaccharides, keep circulating in the blood, and that's how they might reach to the fat.
Wow. And so then there's this spiral. The paper that you published is so comprehensive. It not only has one experiment, but it also has 2 experiments, and it goes deep into the discussion about the biochemical pathways in which she's experienced this spiral of genes that are turning on and off to communicate with insulin. Can you delve right over the deep end? Let's talk about how these challenges or stressors into the dairy cow. How's that changing her day 3, day 7? What did you see in the data?
Experiment 1 asks, what happens to the fat cell when she's exposed to LPS? And the answer, okay, it triggers lipolysis, breakdown of fat. The experiment 2, what does is asking exactly the same question, but see how the response changes as lactation progresses. And we see that before calving, the fat cell is more sensitive to the activation of lipolysis for 2 reasons. One is they have more fatty acid reserves and they can't pump out more fatty acids out of the cell. And the second reason is because they're more sensitive to adrenaline. As lactation progresses, and that's sample 2 and sample 3 at 7 and 14 days, what we see is that response starts to decline. So they release less fatty acids into the system, in this case, into a petri dish. One is because they have less fatty acids in reserves. And the second one is that they start to lose sensitivity to adrenaline and also to insulin too. The second part of that experiment is that we expose those adipocytes to LPS and actually evaluated the response as it affected by the progression of lactation. And the response to LPS was steady. So we don't expect an adipocyte to respond differently to LPS before parturition or after parturition. The only thing that might be more intense is the release of fatty acids because they have more stored before calving compared to after calving. And so that's basically what happens in the experiment 2 of the paper.
Remembering that the LPS is an example of the endotoxin that she experiences just through stressful calving events.
We had essentially 2 questions. The first question was, what does LPS do to the fat when the fat is exposed to it? And the answer is LPS induces lipolysis. So it promotes the breakdown of fats in the adipose tissue. The second question is, what happens when that exposure occurs as the lactation progresses? And that's why we had the 3 time points. So what we found is that LPS indeed promotes lipolysis. And when cows, or in this case, the adipose tissue, are exposed to this LPS for too long, what it promotes is inflammation in the fat, and this inflammation induces resistance to insulin. So what's going to happen is that the cows become unable to turn off lipolysis. So they are going to keep losing weight, and they're going to be unable to turn on lipogenesis. So they won't be able to build up fat with all the circulating free fatty acids that they have in blood. So what's showing us is when a cow has a disease such as metritis or pneumonia, she's going to become more likely or more susceptible to a second disease, usually metabolic disease. And in this case, the most common one is ketosis. That's basically what the experiment.
Ketosis is challenging that energy cycle, and she just gets into the spiral of losing fat and not eating, and then confusing her body. So, how do we block that? What did you learn about the genes? Is there any way? Could you speculate? How in the world could we make her more insulin receptive, or how can we prevent this from happening?
Oh, that's a great question. So the paper highlights at least 2 targets that we could actually focus on our treatments. The first one is the classic pathway of lipolysis, which involves the activation of lipase, which is an enzyme that breaks down the triglycerides. Its name is hormone-sensitive lipase. And we can actually inhibit that lipase using niacin. And niacin is available to producers in the United States. You can feed it during the transition period. So what you would do is feed the cow certain levels of niacin. If you talk to your nutritionist, he or she would be able to help you with that, and that would inhibit lipolysis. The second target that we found is induction of lipolysis through inflammation. And that's very important because niacin does not inhibit the inflammatory lipolytic pathways. The inflammatory lipolytic pathways are usually inhibited by NSAIDs. Just think about Banamine or maybe aspirin, but usually for this, you really need to have a very strong NSAID to reduce lipolysis. So those are two targets that we could have, but also highlights the possibility of inducing lipogenesis. So making the cow build up more fat. And there are some nutritional supplements that we could use for that. And the greatest example is supplementation of oleic and palmitic acids. Our university has several papers out where we describe how targeted fatty acid supplementation might promote lipogenesis and therefore reduce body weight loss. So those are essentially the three targets that we might attack, if you will, to reduce this dysregulation of lipolysis around parturition that might be triggered by infectious or inflammatory diseases such as retained placenta, metritis, pneumonia, or any of those.
Fantastic tools. Thank you so much for going into that. So zooming in on inducing lipogenesis or creating that fat by supplementing oleic and palmitic acid, when is that window that you would recommend that you target those supplementations?
Well, research from one of our colleagues' lab, Dr. Aaron Locke, is showing that we should start that supplementation after parturition, immediately after parturition, so in the fresh cow diets. And that's where it's showing results. Cows are losing less weight compared to cows that are not supplemented with those two fatty acids.
Fantastic. Yeah, you just directly control the fatty acids that are present in the blood, and it's not by the demise of the cow, but rather through the diet. And by encouraging that intake, it can be a win-win-win. So later on in the article, you were focused in on the size of the fat globule. How do you control the size of the fat globule in your dairy cows? Is that a body condition score thing, or is that a genetic thing?
Well, two things. The body condition score is a reflection of how big the fat cells are. So if you have big fat cells, you have a cow that has good condition. If you have huge fat cells, you have a cow that's over-conditioned. So it's a way for us as researchers to indirectly measure body condition score in the Petri dish. That's essentially what we do by measuring the adipocytes. And actually, it's a good test for us to know if our treatments that are inducing lipolysis, including the isoproterenol, the LPS, are indeed doing what they're supposed to, induce lipolysis, right? So we measure them.
That's incredible. I'm so used to doing a lot of research in the barn, but we have to have this benchtop research also to understand and guide our efforts in vivo or in life. And so thank you so much for explaining how you are creating those in vivo conditions right there in the Petri dish in the laboratory. It's absolutely fascinating. As I was reading, I couldn't help but notice my mind kept floating to trying to apply this towards human. And then I turn the page and you start talking about some different human research. I just heard a interesting statistic talking about how fatty liver in humans are going to increase over that of death caused by psoriasis. And it's just incredible to me that the transition dairy cow potentially could hold the future for understanding fatty acid mobilization through humans. Do you believe that periparturient cow could serve as a model for humans?
Yes, and there have been some attempts in the past, and they continue to be, to use the cow as a model for certainly for fatty liver and for gestational diabetes too. However, the cow has some differences in the way she responds to negative energy balance and excessive fat in the liver. One is they have a very steady concentration of glucose in plasma. Unlike humans, we see more ups and downs. The cows tend to be more stable. So that is an advantage and a disadvantage. An advantage is because it would help us to actually study how the liver or the fat reacts to changes in insulin sensitivity in the context of normal glucose, not high or not low. The second important thing is that cows are more resistant to inflammation when they are over-conditioned or fat, unlike humans. When we are overweight or when we are obese, our fat tends to have more immune cells trafficking or moving into the adipose tissue. In cows, we see less of that.
Wow.
What we see in cows is that when they are over-conditioned, when they are obese, they mobilize fat at a higher rate compared to a cow that's in normal conditions. So if you have a cow that's 4 to 4.5 body condition score, and you compare it to a cow that's maybe 3.5 or 3, the cows that are over-conditioned, they will lose a lot of weight in the first 2 weeks after they calve. And they're going to have more risk for ketosis, fatty liver. The cow that's in normal condition, she's going to lose less weight because her fat is going to be less responsive to adrenaline and growth hormone, and they will lose less weight. So that's why it's so important to watch for those cows that are over-conditioned. And I know producers out there, they know that a fat cow is at a higher risk for disease. And that's part of the explanation too. And how they differs with humans, some of the difference that we observe.
Fascinating. Well, I'm just absolutely always enamored by that transition dairy cow and all the different systems that are working to get her set off into the right trajectory for peak lactation. Well, Dr. Contreras, this has been very informative. I want to thank you for your time. And listeners, I applaud you for taking time out of your day to better understand these intricate challenges that occur at the cellular level for your transitioning dairy cows. I've really enjoyed our conversation, and this has been the November edition of Dairy Science Digest, which is a monthly podcast project designed to bring the Journal of Dairy Science straight to your ears. Monthly, we highlight peer-reviewed research articles that are in press. Sound science to base your management decisions around is provided by your University of Missouri Dairy team. So please be sure to like, share, and subscribe to get future editions straight to your cell phone. This is Reagan Blewell with Dairy Science Digest, and I hope you have a great day.